So what are the research questions? There are two main research questions that we would be discussing about in our today's talk. How does the KV-IO stack perform comparing against block IO stack? As we saw that KV-IO stack is the notion of this advancement. Sorry about that, just a click on my pencil. As we saw that the KV-IO stack is the notion of reducing the burden on the operating system side, but rather somebody has to do this work, right? We cannot just omit this work. So this work has been now carried out inside the device. So with these two types of IO stack, what are the design challenges? What are the pros and cons? How do they perform? So having this idea of comparison against these both. Second research question that we'll talk about is what can we learn about the internal components and organization of the device to use it more efficiently? Particularly in this case study, we are discussing about the KV SSDs, but you can gather the knowledge and apply it to any device out there. Who knows, maybe you would invent a new device, new storage device of future. So first, let's discuss the impact of management task delegation, because that's one of the major operations, right? We are delegating all this management tasks from the host side to the device side. So inside the device, now we are performing additional management tasks such as key hashing, hash collision management, membership checking, key value data slicing, and iterator management. None of this had to be done inside the block device. We just maintained a simplistic LBA to page translation table where we had fixed number of LBAs with respect to the device capacity. So we were maintaining this translation table of fixed number of entities with fixed number of entities, because also number of pages inside the SSD is fixed. And then we had our index manager, which is the FTL mapping table that we discussed earlier. And we had other operations. Still SSD had other operations compared to hard disk drives, such as garbage collection, wear leveling, etc. So we still have to do these operations of garbage collection and wear leveling even inside the key value SSD, because eventually it's the same hardware, so it has the same challenges. But apart from these traditional operations, we have two new or multiple new things to do. First is now we have the burden of managing this variable number of key value pairs. Each of them could vary in size. We do not know how many key value pairs a workload would issue prior to hand, right? Prior to the workload itself, where we knew exactly how many total number of logical blocks can exist on operating system side in our block IO stack. But in this case, now it's a variable. But our challenge is to somehow be able to map this variable into fixed number of pages, because eventually SSD is a fixed capacity drive, and physically it still has those erase blocks. Each erase blocks has fixed size pages inside that. So how do we map this variable number of key value pairs, each of variable sizes, into this fixed number of pages inside fixed erase blocks of SSD? And in addition to this one major challenging task, we also have to comply or do additional tasks as listed here, plus the traditional SSD internal management task. So definitely more work means more time, and more time would translate somehow to the latency that we measure, right? It's obvious. No work could be done for free. No work could be done without consuming any time. So higher latency latency what we are measuring here is comparing the latency of block SSD with KV SSD for direct 4 kilobytes random reads. And we see that KV SSDs have around 1.7 times higher latency for reads and 2.5 times higher latency for writes. And that's obvious because more data management tasks inside the device. So definitely it will take more time to perform the operations. But still, this is not demotivating to use KV SSDs because what we should ideally be comparing is end-to-end latencies. The whole point of KV SSDs is to reduce the burden on the operating system. In this comparison, we are not even comparing how much burden was it able to reduce from the operating system, right? So it's a kind of unfair comparison, comparing just the device with the device, because this device is doing much more than the other device. So let's compare end-to-end latencies. If we want to compare end-to-end latencies, we can use the KV SSD and we can compare it with any popular key value store. Here we compare in this results that I show on the screen. We are comparing again 3 most popular operations: insert, update, and retrieve. And on the x-axis, what we are comparing is KV SSD with RocksDB as key value store and using ext4 file system, and Aerospikes as key value store. And then we have comparison of different operations such as sequential IO, random IO, and also a specific distribution of IO such as Zipfian distribution. And here in this graph for different operations, we see that when we compare end-to-end latencies, KVSSD is doing really a good job for insert and update operations, where we see that the latency, which is y-axis, lower the better. Faster is always best, right? KVSSDs are able to achieve lower or comparable latency with the key value store, much lesser than RocksDB over ext4, right? And that applies for irrespective of what operation we do, sequential, random, or with a particular distribution, it applies to all 3 of those cases. Similarly, for update operation, again, we see that the KVSSD is the best compared to RocksDB and Aerospike. But for the retrieve operation here, what we see is KVSSD is still doing a good enough job to be equivalent to what we see here for the Aerospike, but not as good as RocksDB in sequential, as good as RocksDB in its response to sequential IOs and Zipfian distribution with some particular skew. But still, if we see for random IOs, KVSSD is doing on par job. So this shows us a great deal of advantage of using KVSSDs with respect to compared with block SSD, comparing the end-to-end latencies. Now, as we know that KVSSD is supposed to manage the indexing of the data or all the tasks related to managing this index of the data inside the device. And with this operation comes the flexibility. There are different ways in which we could index the data. Also popularly used key value stores, there are different key value stores that use this different index. Some of the popular indexing techniques are multi-level hash table, log structured trees, LSM trees, B+ trees, etc. The current key value SSD that we evaluated in this work was using multi-hash tables inside its structure to index the data. So how does it change things, or what is this impact of new indexing scheme inside SSD? Traditionally, for for the key value stores like RocksDB and Aerospike, we have the application that stores key to values, like the application that uses key value pairs. Then we have file system that manages this SS table files and arranges this SS table files into neatly stored fixed size LBAs. And these LBAs are then issued or requested to NVMe queues of an NVMe device. Sorry about that. Yeah. So these LBAs are then issued to the device, to the SSD, and if it's NVMe SSD, then it's issued by NVMe controller, NVMe drive, to NVMe drive over NVMe bus. And inside the SSD, we have this, we can have a neatly stored LBA to PPA or physical page number, PPN mapping. And the size of an LBA could be same as the size of the PPN. Then everything is just sorted out. Easy way to store the data, store and retrieve the data. But now inside KVSSD, we still have the same application, right? We want to support running the same application that's operating or that's using this key value pairs. These key value pairs then are through the lightweight key value API are directly issued to the KV device driver. Basically, these key value pairs generated by application are almost as it is, with some sanity check are given to the NVMe driver directly to the device. Now these key value pairs arrives at the device, and somehow the device is supposed to figure out efficient way to index the key value pairs to the physical location or the physical pages and blocks where this key value pairs can be stored. If this key value pairs are smaller than the page size, we would soon see later that could make our job easier, because then this key value pair could directly fit inside a single page with just one entry in the index that where is this data stored? It's stored on this page with this offset. But a key value pair can be of any size. It can be of variable size, right? We don't have the luxury of the LBA size being equal to the page size here. So a key value pair can be something greater than a page size. In that case, we have to store this key value pair across multiple pages. And then we have to maintain, somewhere we have to maintain this indexing of where this key value pair is stored. So if we have, okay, what data is this page storing? Then we would have, this page is storing partial data of key value pair 1. While the second page, what data is this page storing? It's storing the rest of the data of the key value pair 1. So we have this additional index entries. But all this work needs to be done inside the device. So continuing to discuss the impact, as we have seen earlier that we see no benefits for sequential access over random access for key value devices. That's because if we are using, let's say if we are using an indexing structure based on hash, then as in the order of how key value pairs come, maybe I should leave the marker. In the order of how the key value pair comes, we do not have much flexibility of where we are storing this data. It's decided by the hashing logic of our multi-level hash index. While in the block SSD, where we were running a file system and key value store over a file system has this nice and neat logic of it would invalidate a hash table after merging. It would invalidate the SS table after it merges the older versions of the SS table into the newer version of an SS table all at once. And this invalidation, because it spent some time in organizing this data into this fixed size blocks, LBAs, and LBAs are eventually mapped to the physical pages, the at once invalidation of multiple SS tables could most probably lead to the invalidation of all the pages inside the block at once. So in a way, when we have sequential IOs, because SS table stores the sorted entries, it's way faster to manage these sequential IOs in the traditional structure of a block device running a file system and then a key value store over a file system. But in the key value device, we do not have any such enhancement of sorting the key value pairs, or the hashing logic doesn't sort the key value pairs when it stores the data. So we see that in key value devices, especially for retrieve, as we see that when we run rocksdb over ext4, we see that the performance of sequential is way better when compared to the performance of random IO. We do not see this advantage of sequential with random in key value SSDs. Just an observation to take a note of. Next, a very important factor that we studied inside the key value SSDs that I would like to discuss with you today is impact of index occupancy. Now, we have been talking about this index that needs to be managed within the KV SSD, but how occupied is this index? Would that affect the performance in some way? Yes. So if our index is lightly occupied, so that means that we do not have many collisions to handle. We do not have more number of layers inside our multi-level hash table. And that means whole our hashing index structure fits inside the SSD DRAM. If we have less number of entries within our index. But as in the KV SSDs, we do not control number of KVPs that arrives. So when we have large number of KVPs, then the index occupancy increases. As a consequence of this increased index occupancy, the index size increases. This increased index size may not be good enough or small enough to fit inside the SSD on-chip DRAM. So it can overflow to the physical flash, and definitely an access to on-chip DRAM is much more faster than an access to the flash chips itself. So there we have some additional time. Having this high occupancy could also incur more number of collisions. So the collision resolution mechanisms are themselves could consume some time. So because of these all these factors, we see that when index occupancy is higher, then we see for KV SSDs, the performance would degrade. So here on the y-axis of this diagram, what I'm showing is latency increase ratio between block SSD and KV SSD. So anything one is, it's the same latency, but greater than 1 means the KV SSD has higher latency over block SSD, and higher is not good. In this A, we are showing average latency, while also many of you who have already worked with IO systems, the tail latencies also matters a lot to guarantee our quality of service QoS. So here we are also showing how does this increase in index occupancy matters to the tail latency as well. And as we see for both read and write, we see a considerable proportion of increase for KV SSD.